Junction field effect transistor, JFET. A junction field effect transistor, JFET, is a type of semiconductor device that is widely used in electronic circuits for its unique properties and capabilities. As a three-terminal device, the JFET operates by controlling the flow of current between its source and drain terminals using an electric field created by a voltage applied to the third terminal, the gate. This makes the JFET a versatile and efficient component for various applications, including amplification, switching, and voltage regulation. JFET terminals and types. The three terminals of a JFET are the source, drain, and gate. The source is where current enters or exits the device, while the drain is where current exits or enters, depending on the configuration. The gate terminal controls the conductivity of the JFET by modulating the electric field within the device. JFETs are categorized into two main types based on the polarity of the majority charge carriers: N-channel JFET, where the majority charge carriers are electrons, and P-channel JFET, where the majority charge carriers are holes. JFET operation. Gate voltage and current flow. The basic operation of a JFET involves controlling the flow of current between its source and drain terminals using the voltage applied to the gate terminal. In an N-channel JFET, a negative voltage on the gate creates an electric field that repels electrons from the channel, reducing the current flow. Conversely, a positive voltage on the gate attracts electrons, increasing the current flow. Pinch-off and saturation. As the gate source voltage becomes more negative, the depletion region expands, narrowing the channel and reducing the current. The voltage at which the channel is fully depleted is called the pinch-off voltage, Vp. Beyond this point, the drain current reaches a saturation level, known as the drain saturation current, IDSS. Cutoff and amplification. When the gate source voltage is further increased in the negative direction, the JFET reaches the cutoff region, where the drain current becomes very small. This property allows JFETs to be used as amplifiers, as the change in gate source voltage can result in a much larger change in the drain current. JFET characteristics. Voltage-current relationship. JFETs exhibit a nonlinear relationship between the voltage applied across its terminals, VDS, and the resulting current flowing through it, ID. This relationship is typically described by the JFET's transfer characteristic curve. Key parameters. Important JFET parameters include the pinch-off voltage, Vp, drain saturation current, IDSS, gate source cutoff voltage, VGS, off, and transconductance, GM, which determine the device's performance and suitability for various applications. Input impedance. JFETs typically have a very high input impedance, often in the range of megohms to hundreds of megohms, making them suitable for use in applications where a high impedance input is required, such as in amplifier circuits. Comparing FETs and BJTs. 1. Basic structure. FETs have a gate, source, and drain terminal, while BJTs consist of three layers of semiconductor materials: emitter, base, and collector. 2. Current control. FETs control current flow using an electric field, resulting in high input impedance and low output impedance, while BJTs control current flow using the injection of charge carriers. 3. Polarity. FETs can be either N-channel or P-channel types, while BJTs can be either NPN or PNP types. 4. Applications. FETs are commonly used in high impedance, low power applications, while BJTs are used in medium to high power applications. JFET advantages and applications. High input impedance. JFETs have a very high input impedance, making them suitable for use in applications where a high impedance input is required, such as in amplifier circuits. Good frequency response. JFETs have a good frequency response, allowing them to be used in high-frequency applications, such as in radio frequency, RF, amplifiers and switches. Low noise. JFETs exhibit low noise characteristics, making them useful in applications where low noise performance is essential, such as in audio and radio frequency, RF, circuits. Versatile applications. JFETs are widely used in electronic circuits for various applications, including amplification, switching, voltage regulation, and as part of more complex integrated circuits. JFET schematic symbols. N-channel JFET. The N-channel JFET has the majority charge carriers as electrons. P-channel JFET. The P-channel JFET has the majority charge carriers as holes. JFET symbol. The schematic symbol for a JFET consists of a central channel with a gate terminal on the side. JFET equations and comparisons. 1. Input resistance. The input resistance of a JFET, often denoted as RIN, can be very high, typically in the range of megohms to hundreds of megohms. 2. FET versus BJT. FETs control current flow using an electric field, while BJTs control current flow using the injection of charge carriers. This results in different characteristics and applications for the two device types. 3. Key equations. The JFET's transfer characteristic curve and other parameters, such as pinch-off voltage and drain saturation current, are essential for understanding and designing circuits using JFETs. Understanding MOSFET transistors. MOSFET, or metal oxide semiconductor field effect transistor, is a fundamental building block of modern electronics. These versatile devices come in various types, each with unique characteristics and applications. This presentation will provide a comprehensive overview of the different MOSFET classifications and their construction, helping you understand the nuances of this essential semiconductor technology. MOSFET construction types. Depletion mode MOSFET. Depletion mode MOSFETs have a conducting channel already present in the semiconductor substrate, even with zero gate source voltage. The gate voltage controls the width of this channel by modulating the depletion region near the surface of the substrate. Applying a negative gate source voltage further depletes the channel, increasing the device's resistance. Enhancement mode MOSFET. In enhancement mode MOSFETs, the conducting channel is not initially present in the semiconductor substrate. A positive gate source voltage is required to attract majority carriers, electrons or holes, to the surface, forming a conducting channel between the source and drain terminals. Enhancement mode MOSFETs are normally off when the gate source voltage is zero and require a positive voltage to turn on. MOSFET channel types. N-channel MOSFET. N-channel MOSFETs have majority carriers that are electrons. These devices are commonly used in digital logic circuits and power applications due to their higher electron mobility and ability to handle higher currents compared to P-channel MOSFETs. P-channel MOSFET. P-channel MOSFETs have majority carriers that are holes. While less common than N-channel MOSFETs, P-channel devices find use in complementary metal oxide semiconductor (CMOS) logic circuits and certain analog applications where their specific characteristics are advantageous. MOSFET operation modes. Bipolar MOSFET, JMOSFET. Bipolar MOSFETs, or JMOSFETs, combine MOSFET and bipolar junction transistor, BJT, technologies. This hybrid structure provides advantages such as high current handling capability and low ohm resistance, making them suitable for power applications. Power MOSFET. Power MOSFETs are optimized for high-power applications, featuring low ohm resistance and high current handling capability. They often utilize specialized structures like DMOS, double-diffused MOS, or VMOS, V-groove MOS, to improve performance. Logic-level MOSFET. Logic-level MOSFETs are designed to be driven directly from digital logic circuits without additional voltage translation circuitry. They are commonly used in integrated circuits and digital electronics, where efficient switching and low power consumption are crucial. MOSFET applications. MOSFETs are the fundamental building blocks of modern digital integrated circuits, enabling the development of complex microprocessors, memory chips, and other digital logic devices. Power amplifiers. Power MOSFETs are widely used in power amplifier circuits, such as those found in audio equipment, power supplies, and motor control systems, due to their high current handling and low ohm resistance capabilities. Voltage regulators. MOSFETs, particularly power MOSFETs, play a crucial role in voltage regulator circuits, allowing for efficient and precise control of voltage levels in various electronic systems. Switching circuits. The fast switching capabilities of MOSFETs make them ideal for use in switching circuits, such as those found in power converters, motor drives, and other power electronics applications. MOSFET versus JFET. Construction. JFETs have a simpler structure with a semiconductor channel and two junctions, while MOSFETs have a more complex structure with a metal gate separated from the semiconductor channel by an insulating oxide layer. Gate control. In JFETs, the gate directly contacts the semiconductor material and controls the channel by modulating the depletion region's width. In MOSFETs, the gate is separated from the channel by an insulating oxide layer, and the gate voltage creates an electric field to control the channel. Applications. JFETs are commonly used in low-frequency amplifiers, switches, and voltage-controlled resistors, while MOSFETs are widely used in digital integrated circuits, power amplifiers, voltage regulators, and switching circuits. MOSFET advantages. High input impedance. MOSFETs have a very high input impedance, allowing them to be used in high-impedance circuits without loading the input signal. Low power consumption. MOSFETs, particularly in digital applications, consume very little power, making them ideal for use in battery-powered and energy-efficient devices. Scalability. The size of MOSFETs can be easily scaled down, enabling the fabrication of increasingly dense and complex integrated circuits, driving the progress of modern electronics. High switching speed. MOSFETs can switch on and off very quickly, allowing them to be used in high-frequency and high-speed applications, such as radio frequency, RF, circuits and digital logic. The future of MOSFETs. Continued miniaturization. As semiconductor manufacturing processes continue to advance, MOSFETs will become smaller and more densely packed, enabling even more powerful and energy-efficient electronic devices. Improved performance. Ongoing research and development will lead to MOSFETs with higher switching speeds, lower on resistance, and better power handling capabilities, further expanding their applications in various industries. Emerging technologies. The integration of MOSFETs with other emerging technologies, such as wide-bandgap semiconductors and quantum computing, will open up new frontiers in electronic device design and functionality.